So, good morning, everyone. So, if you can hear my voice and see my shared screen, please type Y in the comments. Okay, so then we'll proceed. So, yesterday we had a very good discussion on k-means clustering, how it basically works. We'll go into the mathematical formulation today of k-means clustering and also discuss uh, very efficient algorithm or efficient algorithm or very more popularly used algorithm with respect to the traditional k-means clustering called the LBG algorithm. So we'll discuss these two aspects today. So let's get started. So we had said yesterday that we have a d-dimensional feature. There is a feature set containing of n feature vectors. Each feature vector is d-dimensional, and we need to arrange them or find out the clusters within them. The number of clusters we predefined it as k, which we call as a hyperparameter. Hyperparameter. So, so let's start with. We have like this. Imagine x1. All these are vectors. X2, x of n. We can represent this set as a set of feature vectors. We can represent it as a complete data set or feature set, whatever you want to call it, feature set or data set. Each is d-dimensional, and we want to arrange them into clusters. Okay, we can say clusters k equal to 1 to k. Now, what is the representation of of these clusters? What is their identification or representation of these clusters? These clusters are identified by their means. We can say for every cluster, there is a mean associated with this, a mean vector. Each cluster has a mean vector. Remember, these are all vectors. So, and we need to associate every point. Some nth point is there. Every point we need to associate with a cluster. So if this point xn belongs to a cluster k, some k, then it will be 1 and we'll assign it a value 1. We have presented a variable rnk such that if this, what it means that if the point, the data point, which also means the vector n, if it belongs to the cluster k, then we'll give it xn belongs to cluster k. Otherwise, so you can imagine something like this. For every, if you n in this direction and k in this direction, So RNK, maybe you can denote it by a matrix R or something. Matrix RNK, you can say probably. So you can have, for example, some data point n, 1 to n. Okay, so it could be that, let's say there are three clusters: 1, 0, 0, 0, 0, 1, 1, 0, 0. So associated with each point, there is a variable RNK which tells us that tells us which cluster this point belongs to. So these are the notations, and we need to find this for each and every data point, and we need to find this. What are the centroids which represent the clusters? Centroids or means which represents the clusters. So let's now look at means we call this. So how to go about this process? Every machine learning algorithm will have something called as an objective function or a loss function, also called a loss function. What we try to do is we either try to maximize or minimize this loss function subject to certain constraints. Sometimes those constraints are there, sometimes no constraints are there. So in our case, let's see what the objective function is. So just imagine this, and we have found, let's take another color. So there is green colors are the mu. So this is your mu2, this is your mu1, representing the clusters. So suppose are properly all the points are properly associated with their clusters and so on. So you will find then this all this the distance between a particular point and its cluster is the minimum. Obviously, let's say this is x1. X1 minus mu1 will be much lesser than x1 minus mu2. This distance is so this distance is far lesser than this. But if it was incorrectly classified, incorrectly, so suppose this point, let's say this point is x2. If it was incorrectly classified, yeah, associated with cluster 2 instead, so let's say this cluster was something like this, and we now take the distance of this point from the different clusters. Even then, you will what will happen is this. Let's put it as x2. This x2 minus mu2 is greater than x2 minus mu1. So if the data points are correctly classified, its distance from its associated cluster is always going to be less compared to its distance from all the other clusters. So this we can use to our advantage. So if the clusters are properly classified, if the clusters are properly formed, clusters are properly formed, Then any this distance, this is the minimum distance. So a point, the distance of a point from its associated cluster is always going to be minimum, provided this R and K you have correctly associated, provided the point is correctly associated to a cluster. So for if like a point n or data point n or vector n is associated with the cluster K, then this is the notation to get the distance. If it is not associated with the cluster K, then R and K will be 0 and we will not get any value. But if it is associated with the cluster K, this is the distance you get. So for each and every, for a particular point n, for a particular point n, you can find out its minimum. You can say if the clusters are properly formed, this is the distance of the cluster from its for the point from its cluster. RNK will be 0 for the clusters which is with which it is not associated. Only for the cluster which with which it is associated, it is going to have a value of 1. So this gives the distance of a point from its cluster. And then for all the points, you can find out this distance. This is going to be your objective function, generally denoted by J. We will try to minimize, our goal is to minimize this objective function with respect to RNK and with respect to mu k. If the points are correctly if the points are correctly associated with the clusters, then J will be obviously a low value compared to if it is not correctly classified with the clusters. Again, if the cluster centers are appropriately defined, then this J will be a low value compared to if the cluster centers are randomly defined. If you have data like this, if the cluster centers are somewhere here and here, obviously J will be very high compared to if the cluster centers are here. This objective function will be low. So our goal is to minimize the objective function with respect to these parameters. So now this vector, if you represent it in Euclidean, these are all this is a vector. So this Euclidean form, okay, this is a Euclidean distance. You can represent it as like this. So J, you can represent it as n equal to 1 to n k equal to 1 to k r of nk xn minus mu k transpose xn minus mu k. You figured out why this is the case. It is a simple mathematical way to represent this. And just like in uh, just like in scalars, suppose these were not vectors, then this will be become a square, xn minus mu k whole square. If this was a single dimensional vector, that means a scalar. If the features were single dimensional, this will become xn minus mu k whole square, and these will be all be scalars. But you can this vector calculus is a simple vector calculus. So, but exactly like if you have x square del x of x square, what will be 2x. Similarly, this here, what will happen is if you try to do del of del rnk, you will get nothing. Let's do this. Let's take a particular n naught. Okay, n equal to 1, 2, something n, and our k equal to k. Let's take a particular n naught and a particular j. Okay, and del j by del r n naught k, n naught j. Let's try to do it. Then if you unwind the j, it's all summations. You'll find that the only thing remaining is now to maximize, you have to put the derivative to 0. And here you don't get anything. This result is a meaningless result. So what it is saying is your data point equal to mu, this cluster J. But it is a meaningless. There is no Rn not variable here, so it's a meaningless result. But what it so this gives no output basically. This optimization function does not give out, but you can figure out indirectly what it means is even logically you can figure out. So what we are trying to do, what is the best thing to do here is you just assign. So what does this mean? So what it means is this in mathematically. So you compare xn with mu, sorry, this should be with mu j. That is the centroid of a cluster, and you vary j. That means you vary the centroid of the clusters, and you get a value. So since there are k centroids, you will get k values. Whatever the value of this variable j you have chosen, which gives you the minimum. This is called argument, argmin, not min. This is argmin. Whatever the value of this, whatever cluster basically gives you this minimum, that cluster number you assign it to k. So if k becomes the same as whatever, you get from this mathematical expression, you put Rnk equal to 1. This is a clever way of mathematically representing what we are saying, that we should assign a point to a particular cluster. This is a appropriate mathematical notation for that. And how do we, means we indirectly get to it, because if you see, if we, sorry, if we try to do a partial fraction with respect to Rn not j, Rn not j gets cancelled, means there is nothing, Rn not j gets uh, cancelled or removed from the equation, and then we cannot derive any solution for Rn not j. We are left with this term which says that x and not should be equal to mu j, which is true. Means if your centroid, if your data point is equal, is the same as the centroid as you have chosen, that then indirectly it is saying that your data point and your centroid must be the same. Of course, that cannot happen. We have finite number of centroids. So the logical solution is that we will choose the nearest centroid, the closest centroid. Now coming to del j by del, yes, mu. Let's take mu j. So what will you get if you look? If you look here, as I said, it will become, remember this term. So you will find, if you go to the mathematics, it's very easy mathematics, but you can have an this is analogous to what happens in scalar, in case of scalar calculus. This is analogous to that. So we'll find that you are left with a term uh, xn minus mu j. I think that should be the, let me check. Yes. Yeah, so mu k, so this n term is not affecting. We are only deriving with respect to this parameter, so n remains as it is. So this is what you will end up with. Yes, there is a, I forgot, Rnk was also there, R of nk. And if you put it to 0, because you want to minimize, so you will get Rnk xn equal to Rnk mu j. N mu, yeah, j, n equal to 1 to n, n equal to 1 to n. So here mu j is not associated with, there is n is the variable here. So you will get mu j equal to n equal to 1 to n Rnk xn by this n equal to 1 to n Rnk. So let's talk in detail about this. So we get mu j equal to r of n k, n equal to 1 to n, x of n. So what does this mean mathematically? What we found by mathematics. So where j equal to 1 to anything. So any point, sorry, this should be Rn j. This will be Rn j. This will be Rn j. Please, when you do this, I, I would say please be careful with these notations because we are doing with mu j. Be careful with the notations. So, uh, so what we have, if xn, if xn belongs to this cluster j, then Rnj will be 1. So for all the data points, we are summing this up. So we are basically summing all the data points belonging to the cluster J. Because xn, if it is not belonging to J, it will be 0. Only if belongs to J, it will be this Rn and J will be 1. So only those points which belongs to the cluster J, we are summing up. And what is below? We are summing up basically what are the number of points. This is the number of points belonging to the cluster J. That is what it is happening. Because Rnj is 1 only if a particular point n belongs to the cluster J. So this is the number of points belonging to cluster J, and this is the sum of all the points belonging to which belongs to cluster J. But that's what we have been what is it called visually we visually demonstrated yesterday. So finally, what is the algorithm? This is a mathematical way we have described. So finally, the algorithm goes like this. Sorry. So algorithm is step one, initialize clusters. How many clusters? K. Initialize K clusters, which we define beforehand. Each cluster is associated with a center. This could be random or intelligently initialized, but it is initialized. Step 2, repeat iteration. I equal to 1 to whatever till convergence. So part A of that, what will you do? You will associate one associate which data point with a cluster. Second part. Now, this is the iteration number. For any cluster, how will you get? You have got from the previous assignment. Sorry. So these 2 points you keep repeating, and then C, determine J. So these 2 steps I will do. So for step A, you assigned the data points. Step 2, you can put it JI. Okay. Step 2, you can put it mu KI here. I forgot. Okay. Step 2, even here also you can maybe you can put it I. Let me go back here. You can put it I here. Okay. That means the iteration I, you are seeing what is happening. Okay, mu j, you can put it I minus 1. So in the ith iteration, your previous is whatever you are already having the cluster means, you are comparing against that for assignment of the point, or rather reassignment of the point to the clusters. So then you have, you can put here again, once you get the reassigned points, you find out the new cluster means, then you find out what is your uh, current optimization or loss function value, and that way this goes on, and you will find, or you should find, this is n equal to 0. Sorry, let's put I, iteration, and this is j. Fine, like that. J will decrease as the number of iterations it, and here you could stop it, stop the algorithm. As the number of iterations goes on, you could put a check that if j of ith iteration minus j of I minus iteration is not changing much, is less than some epsilon value, very small value, then you stop the algorithm. You can do that, or you could check, this mu k ith iteration minus mu k I minus 1 iteration is less than epsilon for all, for k equal to 1 to k. You can stop then also, but this is the easiest way, because here you have to do so many checks. Here only one check you do. This is the way to iterate. On top of that, you could also say n equal to 100 or n equal to 20, sorry, I equal to 100 or I equal to 20. That is the maximum. We will not iterate more than that. You can also fix a number that I will iterate this algorithm and for this amount of time, and it will continue. It will end after that automatically. Now, question is, yesterday somebody asked, how do you find out the value of k? So what you do, what should be the k, the hyperparameter we initially this one. So you do this process for k equal to, let's say, 2, 4, 8, 10, like this. See, at the every algorithm, you will have a j. Whenever your algorithm ends, a final j value you will get, final optimization function value or loss function value will get. So you will find something like this occurring. It does not increase, sorry, it never increases. It will go like this. But you will find that after a particular point, this loss function is becoming saturated. So increasing the value of k is not having any effect, much effect. So this is also called knee point, is a fancy term, but basically the j, the optimization function, if you do this k-means algorithm many times in the data set with different hyperparameters, you will find a particular knee point or a particular value of k after which the optimization function is not changing, or it's, we call it saturating. The change is very little. That is the way to figure out what should be your hyperparameter. That is how you figure out what is your hyperparameter. So I thought about covering the LBG algorithm. I don't know, there is not much time, but let me now uh, discuss about one or two issues with the K-means algorithm. Before that, I just again want to show you this. I think I picked this from a very popular machine learning book. It's called Pattern Recognition and Machine Learning by Bishop. It's a very popular and a very wonderful book, actually. I took this figure from there. So what it is showing, yesterday I was trying desperately to give you this idea. So these are the center means initially at zero iteration, initialization. And these are the two clusters, you can see the clusters. So what happens is, first reassignment of these points to these clusters, yellow points to yellow cross, and green, it is blue points to blue cross. Then we have in the first iteration, this is the first iteration, iteration 1, I equal to 1. So you have then step B, step B 2b. If you go through your slides before, you will understand in the recorded lectures. You will have now recalculation or re-evaluation of the cluster means. Then based on this cluster means, you will now have again reassignment of the data points. This is your second iteration. And then again this process keeps continuing. This is step 3 and so on. You can see now after this point, after only 3 iterations, it's after 2 iterations, now these things are started slowly beginning to converge. So you will find, if you plot j in this case, and here is your iteration, you will find that after let's say 2 iterations, it will start to become flat. It will start to saturate. This is an example of an image here. I think okay, let's not go to into this. So yes, so what is the disadvantage? The disadvantage, we'll look into this again when we study Gaussian mixture model tomorrow. The disadvantage, however, you see, if your data is, the clusters are not circular, concentrated in a circular fashion, the k-means is not very effective. You can see here for data like this, where you can see there are two different clusters. This is one is one cluster, the other one, but k-means is not able to work properly. There are ways and means to circumvent this problem, but still, when the data is not concentrated in a circular fashion and removed from each other, it is not like this. K-means does not work very well. On top of that, there is another issue which we'll probably discuss tomorrow. Suppose you have a cluster like this, and you have another few points clusters like this. There's a big cluster, there's a big cluster, and there is a small cluster. Now obviously you will find a big cluster center point is here, the small cluster center point is here. So one cluster is a little bit spread out, the other set of data points is a little bit more concentrated. The phenomena, the natural phenomena is like this. It is not in our hand. That is what it is. But you see what will happen to a point here. It seems this point will be associated to this cluster instead of being associated to this cluster. So K means clusters, it forms clusters with equal radius. You can say it forms clusters with equal radius. If you have a point in between, it's also in the range of this cluster, also in the range of this cluster. It forms clusters of equal radii, actually, radii. If there was another way that we could not only associate the mean, but its control also the radii, indirectly the variance, then we'll have a better control. If we could model not only the mean with every cluster, not just the mean, if we could model the variance also, then it would have been a much this problem could have been circumvented. But as it is, k means is only modeling the means, and hence it is not suitable for clustering data points which are clustering data in which are having large and small clusters, whose cluster radii are varying to a large extent, because each cluster has equal power, equal sphere of influence around it. There is no way to control or model the variance or radii of the clusters in caves. That is the significant, no way to model variance or radii of the clusters in k-means. That is the significant drawback. Apart from what we saw earlier, that it generally models only circular clusters, which is good in modeling circular clusters, which are isolated. For other different shapes of clusters, it is not very good. So that's all. We'll discuss about LBG and GMM in the coming classes. What I would like you to do, uh, let me see where it is. There are two very good videos in YouTube demonstrating the k-means algorithm along with some mathematics, and also Python they have implemented. Python script they are showing, demonstrating. So you can go through that. It will be good visual. Sorry, it will be good for your understanding. So that's it for today. Please give your attendances, and we'll end the lecture now. Please exit the lecture. Yes, so good morning, everyone. So if you can hear my voice and see the shared screen, please type Y in the comments. Okay, so then, as usual, we'll proceed. So we were discussing about k-means algorithm in the first lecture. We visually tried to understand what k-means clustering algorithm does. And yesterday we gave a kind of a mathematical formulation of that, kind of a mathematical derivation, which was quite simple, to be frank. Now, towards the end, we were discussing about some disadvantages or limitations of k-means algorithm, and to counter at least some of those disadvantages, revised version of k-means algorithm called LBG. LBG is the name of the authors. I forgot that. Please check it out uh, over the internet. That LBG algorithm was proposed. It's a very simple but effective algorithm. But let's now go ahead with again recapitulating the principal drawback of k-means. So we have here what happens in k-means. There are, let's start with the plot number A. We have, you see, you can see that there are two clusters here. So we start with some randomly chosen means as the cluster centers. Then in the first iteration, we do these two steps. Each of the data points are assigned to one of the clusters depending on which one is the nearest or which one is nearer. So once you get the data point assigned to a cluster, from those data points, you recalculate the means of the clusters. This is I equal to 1 here. This is the first iteration occurring. Then from those new means, based on these new cluster means, you reassign the data points. Again, recalculate. This is your second iteration, and similarly it will go on. Now the problem here is, I was discussing, suppose there is a lot of data points and there is a small cluster, means very close knit cluster, you can say. There is a cluster which is quite you can say it has large variance in mathematical terms, statistical terms, and there is a small cluster. You can see there are two different clusters, but this point, the cluster mean, let me denote by another. This is the cluster mean here. This is the cluster mean that will form. What will happen to this point? Maybe I can take another, or this point. It seems because the way the K-means algorithm works, these will be assigned eventually to this cluster, even though it does not seem right. So this is because the K-means, in K-means clustering, we only model the means. We don't model how big the cluster is. Indirectly, we call it variance, or actually, when we will discuss Gaussian mixture model, we should talk about covariance. We denote covariance by sigma, although it this same sigma is used for summation. It is a bold, it's a matrix. It's called a covariance matrix. We'll discuss GMM after we finish K means. So there you will encounter this sigma. So we don't model the variance, or indirectly we don't model the what is called how big the cluster is. That information is not modeled. On top of that, there could be some clusters like this. You could have a data set, feature set, which is like this. This flexibility is not there. You see, it has a kind of a rotation. It has a direction. The cluster has a direction. If you model this by K means, say, even if it is accurately model it, it will come out like, sorry, at best, the clusters will be like this at best. So when you include this covariance in your models that we do in Gaussian mixture model, then you can incorporate all this information and you can make it a more well-rounded clustering solution. You get a more well-rounded clustering solution. But now we are still discussing k-means, so let's stick with it. So this is one of the problems, that all the clusters have kind of equal ability to pull a data point towards one another, because the uh, width or the sphere of influence of the cluster is not modeled. The sphere of influence, you could say, or the variance or the radii of the clusters are not modeled. That is one. Now there is another thing. This is typical. This problem is typical of most machine learning algorithms. You see, J with respect to I. Okay, as iterations. This is the loss function. J is the loss function or optimization function. So as iterations increase, I equal to 0 means 0 iteration. You did not do anything, just randomly you selected the cluster centers, and based on that also you can find out the optimization. Then one, first iteration, second, like that you. So if you see, let me go back and see where is the uh, I should be able to. Yes, so I have written many times this. So this is a quadratic. This is a quadratic equation. See, it's square. Quadratic means power of 2. A polynomial which has a power of 2 is quadratic. So this is a quadratic equation. The quadratic equation always looks like this generally. It looks like this. But of course, with we have seen that it's always going to or decrease or something. It will saturate. But what happens is sometimes it could go like this because this is real data. This is real data. So depending on each and every iteration, you select new means and reassign data points and so on. It could happen like this. These are called local minima. Local minima. These points are called local minima. And this is your global minimum. Your goal is to reach the global minimum. But it could happen that you get stuck in local minimum. This is a classic problem of all machine learning algorithms. And the reason this why you get stuck in the local minimum or global minimum is generally associated with you have how you choose your initial data this cluster means. What is the initial, how have you chosen means you generally choose, if you choose randomly it could happen that you get to a situation like this. So to take care of this particular problem, that not to get stuck in local minima, a slightly refined but very effective solution was proposed, and it's called the LBG algorithm. So let's go to LBG algorithm, what it does. So there are some points, and there are, let me put circles here today. These are the points. So the LBG algorithm, for the LBG algorithm to work, this K has to be, there has to be like 2 to the power K clusters. K cannot be just a simple integer. So the number of clusters has to be 2 to the power k. So it could be 2. One cluster does not make any sense. So it could be 2, 4, 8, 16, 32, like that. Why you will come to know, but there has to be 2 to the power k clusters. Instead of any random integer in k means, we could choose any random integer. We need to have 2 to the power k clusters. That's the first point. Now let's go about how to do this. So the first thing is we will say k. So k will vary from some this this small k I am talking about. Okay, the small k will vary from 0 to k, and your cluster size will vary from clusters. Number of clusters will vary from 2 to the power 0, 1 to 2 to the power k when the algorithm will be completed. So this is another advantage. You don't need to figure out when to stop the algorithm when convergence occurs. But the disadvantage is or limitation is you need to have this amount of 2 to the power something number of clusters. So in the first, when k equal to, we'll put k equal to 0. This k now becomes synonymous with your iteration. The number of iterations will be k, this number k. There are 2 to the power k clusters. So the k number will give me your number of iterations. So the first 08 iteration, you just, the cluster mean, you just pick the mean of the data set, whatever mean of the data set. Whatever mean of the data set, I will probably denote mean as star to avoid confusion. Mean of the data set, all data points are obviously assigned to that cluster, cluster mean. So in k equal to 0, this happens. In k equal to 0, all data points are assigned to C1. Number of clusters is 1. In k equal to 0, number of clusters is 1. 2 to the power 0 is 1 equal to 2 to the power 0 equal to 1. And all data points are assigned to the clusters. Mu1 you calculate from all the data points. Now you add in k equal to 1. Let me go to, okay, here only I can do it. At k equal to 1, what should be the number of clusters? 2 to the power 1 means 2. So what we will do here is we'll create mu1 plus epsilon, sorry, mu1 will give a small, very small number we'll give, and we'll create two cluster means like this. So C1 will be, so you can say mu1 1 now equal to mu1, let's put it 0 here, mu1 0 minus epsilon, and c2 equal to mu2 equal to mu1 plus epsilon. So you get two cluster means. So what you have is, this was your mean. You created two means basically. This is called mu1, mu2. I will mu1 1, mu2 1. I will call them because it's k equal to 1 where you will create that. Now you use your traditional k-means algorithm. You have two clusters. If you use k-means clustering on this, what will happen? All these points will be associated here. All this will be associated to this. Then you recalculate your cluster means. So reassign data points as per k-means, recalculate cluster means. So you will get a new, you can say a new. Better to call this new, I think. How many will you remember? What is called keeping track of all these numbers will create problems. So uh, new, you get your new means after reassigning data points and recalculating cluster means according to k-means algorithm. So let's go now to step 3. Now k equal to, oh sorry, in our case there were two clusters only. That's finished. Your algorithm is done. Its algorithm is completed. Now let's take a few more clusters so that we can take this idea further. Let's say there are some clusters here, here, and again something, and again something here. Let me put all of them the same. Let's say here, 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 something like that. The first, so there are, you can see there are four clusters. So let's assume we know that there are four clusters, or we want to divide into four clusters. So k equal to 0, 1, 2. The number of clusters we'll get as 2 to the power 0 means 1, 2 to the power 1 means 2, 4. So in 3 iterations, we'll finish this job. So k equal to 0, we'll get a mean from all the data points. All the data points are assigned to this cluster 1. all data points belong to cluster 1. All data points, whatever for n equal to 1 to n, all, then k equal to 1. We create two clusters now, mu1 plus or minus epsilon, whatever you, and mu1 plus epsilon. So if this was your, sorry, this was your cluster, you split it into two parts. It comes here and here. So this is what you get. Two you get. So from this, obviously you will find what will happen after k-means. If you run k-means on this, most probably something like this will happen. Something like this. I'm just hypothetically, all these points will come like this. Most probably. These are the data points that will come to both the clusters. Now we go to k equal to 3. Or maybe I will use another page. So at the end of the k equal to 1, that first iteration, what we found is, let's say something like this and something like this. Let's assume for the moment. Now we will split at k equal to 2. What we have? K equal to 2 means 4 clusters. Number of clusters is 4. Equal to 2 to the power 2 equal to 4. So we will split this C1, C2, C3, C4. How will you get C1, this one? From here, whatever was initially C1, whatever was this mu1 you got at the end of k equal to 1 algorithm. So mu1 minus epsilon, mu1 plus epsilon, mu2 minus epsilon, mu2 plus epsilon. This is your mu1 new, mu2 new, mu3 new, you can say mu4 new, whatever you want to call. Or maybe we'll not name this like this at the moment. So let it be like this. Some other notation you can use. But you have effectively now split it. What happened is, so you have created now 4. 4 of them you have now created. Now with this initial now, these are your initial k-means clusters. Now run the k-means clustering algorithm on this. What will happen if you run it? All these data points will be assigned to this one. All these data points will be assigned to this guy. All these data points will be assigned to this. All these data points will be assigned to them, and then you, according to k-means, you re-evaluate the cluster means. So you will get ck, you can say whatever, c1, c2, mu2 new, c3, mu3 new, c4, mu4 new. That's it, your algorithm ends. So your new clusters will be, so in this manner you can use the LBG algorithm and get rid of the initialization problem, the local minima problem of k-means. So this entire process is called the LBG algorithm. So uh, maybe we can write it down. Sorry, LBG algorithm. We divide the data set or feature set into 2 to the power k clusters, where x is the data set, where x1, x2, xn, and xi belongs to r to the power d dimensional. Each one of them, and like xn, maybe I should put, we have been using xn. So it's a d-dimensional vector, each one of it is. We have, we know all this. So step A is for k equal to 0, there are 2 to the power 0, 1 clusters. All data points belong to one cluster called C1. All data points belong to C1. Mu1 is simply the summation of all data points. Then step 2, for k equal to 1 to log of 2, or k basically, big K. Number of clusters is c to the power k. So we divide uh, mu1, any c to the power k. So let's give it a name j for, let's say, any old cluster that was there. If mu j is a cluster mean from the k minus 1 iteration, then we'll split mu j into two parts. And finally, we will get mu1, comma mu2, comma mu3, like that. Mu of ck, number of clusters is ck, where mu1 equal to mu1 of k minus 1 at iteration plus epsilon or minus epsilon, and mu2 equal to mu1 of k minus 1 at iteration plus epsilon. Similarly, you can show some a mu3 equal to mu2 of k minus 1 at iteration minus epsilon, mu4 equal to mu2 of k minus 1 at iteration plus epsilon, and so on. You can write a few like that. So now what you do next is step 3, or maybe that step 2 itself we can later on we can proceed. Run k-means algorithm with x the feature set and mu equal to mu1 to mu ck as cluster centers. So then you will have obtain rnk for each data point xn. This is rnj, I should put it, maybe rnj for each data point xn, and cluster cj, where j equal to 1 to ck. You can put it like that. T reevaluate cluster means. So mu new equal to mu1 new mu ck new. So this is LBJ algorithm. So I wanted to start Gaussian mixture models today, but before that, I want to the in machine learning, probability and statistics is absolutely imperative. There is no way out. So you have your exams this week. I will give you another week after that. You submit an assignment. I will see if I can take that assignment instead of any test, if it is possible. You submit that assignment or review your probability theory. And whatever I have discussed regarding that k means this, even the LBG algorithm, it does not it makes it overcomes some of the problems of k means, but it does it ultimately the problem that k means has no control over the area of influence of a cluster. No modeling of variance is included in k-means. That problem remains in the LBG algorithm. That problem is not overcome. So we need to go for something called as Gaussian mixture model. So what I would like you to do is I am giving you a few links, YouTube links of Gaussian mixture model. Go through them so that you get a idea visual idea of what's happening. But more importantly, these videos are about Gaussian picture models. Maybe I will share them again when we are discussing the topic. You can just go over it and get an idea. But more importantly, probability and random process you must revise, and I will give you as an assignment to submit. I would suggest, my suggestion is uh, get the PDF copy of the book Pattern Recognition in Machine Learning. I'm typing in the comments by Bishop, Christopher Bishop. In, I think, the first or second chapter itself, maybe the first chapter, I think, it's a big chapter. They review the entire probability theory in a very concise manner and in a very effective manner that you will need in machine learning. So get a PDF copy of that book, ebook or whatever, and I would suggest go through that first chapter where they review probability theory and other certain things such as decision theory and all. These are simple things. If you know Bayes theorem, you'll be able to follow all that. This is not difficult. But you must review that so that we can go to Gaussian mixture model and then hidden Markov model. And even deep learning and all, everything in machine learning requires a good sound and knowledge, or you need to be sound and comfortable with probability and random process in order to work in or understand machine learning effectively. So that's all I have to say. Yesterday I shared some videos on K-means clustering algorithm. Go through them again, and uh, if possible, go through some of these videos on GMM. But before that, I don't know whether you will understand it. Before that, you must go through probability and random process. I will give you an assignment based on that, which you need to submit after your examinations this week. So that's it. Uh, Please give your attendances and please exit the lecture.